Meeting is being recorded.
Okay. Hi everyone, thanks for coming once again to the AstroAI lunch talk. We have today Atilla Alkan, who is a postdoc right here at the CFA working with AGS. He's a computer scientist and expert in natural language processing, and he's going to tell us today about beyond abstracts and full text, investigating optimal input representations for multi-label scientific document classification. The floor is yours.
Thank you very much. So good morning, everybody. Yeah, today I will present my work that I'm conducting at ADS. So it's about natural language processing, classifying documents in astronomy, and so on. So just before that, I'll give you a bit of context. So we are ADS. Now today we are called SciX. We're transitioning to a new platform where we are indexing more papers coming from different domains, not only astronomy, but also from the earth science, heliophysics, and many other different disciplines. So we're expanding it. And as ADS, one of our main objectives is to be able to structure the information, extract information from the literature, and structure that information into a shareable knowledge. So type of various tasks that we're doing it's, for example, classifying papers, as you can see on the left. When authors submit papers, we want to know if this paper is about astronomy, about planetary science, earth science, or other more fine-grained system that we're trying to build. It's entity recognition for information retrieval and information extraction. So basically, when we have a paper about gamma ray burst, for example, we want a system being able to detect which gamma ray burst is discussed in the text, what are its coordinates, and many other physical properties about that. And other task that we're trying to do, it's concept detection or concept assignment. So when we have a paper about astronomy, we want to go one step further and we want to know, okay, what are the methods described in this paper? What are the simulation? What are the core concepts discussed about this paper? Are we discussing about celestial phenomena such as supernova explosions or black holes and so on? That's what we're trying to do. And this, the focus of this presentation will focus on this aspect, on this task of concept assignment. So in astrophysics, a paper covers usually multiple topics simultaneously. So you can have a paper that will discuss about star formation, spectroscopy, and neutron stars. And in computer science, in computational linguistics or natural language processing, usually we model that task as a multi-label text classification task. So basically you have a set of labels, a set of concepts, and we are trying to learn a scoring function where, given a document, we will try to predict if a label, among the set of labels that we have, those that describe the content of this paper. And basically, our output is a probability vector where each probability corresponds to the relevance of one concept, of one label that we have in our label space. So that's a very challenging task in the sense that the labels we have comes from the Unified Astronomy Thesaurus that is composed of more than 2,000 labels, if you're familiar with the UAT taxonomy. So we have 2,000 labels. And when we look at a bit our data set, we can see that most concepts, so we have a long tail distribution, a lot of concepts. Here I have the distribution. So I categorize the labels into different categories. Tail labels, which means that they occur there is less than 10 training samples in the training set here. So we have a lot of labels that are extremely rare. And if we look at the head labels that occur more than 100 times in our training set, we have 164. So only few labels appear several times, and most of them are very rare. So which means that in average we have like 4 to 5 labels per document. These are the labels we're trying to predict, and that's very challenging because the classifiers needs to see several examples to predict these categories. And as if that problem wasn't enough, we have another problem, which is the input itself. Most of the time, when you look at the literature, how computer scientists deals with this problem, most of the time they will use as input either the title or the abstract or the combination of the title plus the abstract. And based on that, they will try to train a system to perform prediction. But these are relatively short input, and they don't have enough signal for the model. They don't bring to the model enough signal about the content of the paper to predict the relevant concept, the relevant keywords. And if we want to use like the full text paper, that's also a bit of a problem because the full text is long, it's a bit noisy, and it exceeds our language model capacity because we are using here an encoder called BERT. I don't know if you're familiar with language models. So it's limited to 512 tokens, let's say words, 512 words, and the paper is usually like 10,000 words, very long. So it exceeds the budget of our language model. So what I try to investigate is try to see, okay, we have the abstract, which is too short, doesn't have enough information, and the full text that is a bit long. So can we try to find an intermediate here, a representation that is both compact, which wouldn't exceed the budget of our language model, and which is also concept complete, that would have enough info that would be rich as the full text paper, but more compressed. Yeah.
So I'm interested about the abstract not hitting the sweet spot, right?
Yeah.
So is that true for all abstracts? Like for instance, ANA has a very structured abstract that has like it tells or yeah. Have you seen like discrepancies in like different ways that abstracts are written in the sense that like maybe we can push that to the right?
I mean, for example, most of the abstract are, so yes, they're human written a bit in an unstructured way. It's not structured. There are some publishers, I guess, I don't know if it's still the case, they want to have like a bit of a structured abstract where the abstract is a bit more comprehensive and organized, but this is not the case for the whole corpus we have. So, and that's a phenomenon that I noticed only on few journals, not in a lot of papers, and I don't know if it's still a practice, so I don't know if it's still done. But most of the time, the abstract is relatively short and very compact, and it doesn't contain all the information we're looking for.
So can we write our abstracts better to optimize that?
Ideally, if we can push that to the authors to have a more comprehensive, like to provide them not instruction but guidelines to write abstract differently, that can be a good approach, actually. Yeah.
Okay, maybe I'm getting ahead of your talk, and so you can just maybe wait. Did you explore or think of any other strategies rather than truncating the body? Maybe asking, oh, what is this figure about? Or asking for a structured, maybe longer thing for an LLM to do from the full text.
Yeah, so we tried several experiments. We tried different approach. For example, we give the full paper to an LLM and just ask to provide the most relevant keywords. But usually what we notice is that the LLM will tend to provide very generic terms that are not the one that really describes the core phenomenon that is described in the paper. I can try to give an example. If the paper is about radioactive galactic nuclei, maybe the LLM will predict active galactic nuclei, which is a broader category, which is still not wrong. But if we want to categorize the paper in very fine-grained categories, we want to have the narrower concept detected. And usually the LLM has this tendency of predicting generic categories, while we want more fine-grained categories. And here, when we truncate actually the full text, I'll explain in our experimental protocol, like in our experimental settings, that the full text is too long, so we will separate into different chunks, and I'll explain that in a bit. So, okay, the question, I will just remind the question here. So can we construct an intermediate representation that is both compact as the abstract and complete, concept complete as the full text? That's what we were aiming for. So initially, a few months ago, I released a paper with this AstroConcept dataset where I established first baselines with non-parametric approach where, for example, I trained a nearest neighbors approach and try to see how a nearest neighbors approach can perform when it comes to predict the keyword. Basically, the idea is here you have a new paper. You will check on the embedding space what are the papers that are the most similar to the current paper we want to predict the keywords. And we'll check at the neighboring keywords. We'll see that our neighbors have majority this type of labels, this type of concept. So we will use the neighbors labels to categorize our own paper. And here we can see the precision recall and F1 score when we perform this way. So I don't know if you're familiar with precision recall and F1 score metrics, but usually the recall is among all the information we want to collect, what's the proportion of the information we gathered, and among the extracted information, what's the quality of our prediction, the quality of the labels. That's the precision, and the F1 score is an average between the precision and the recall. So we can see that it's a score which is usually between 0 and 1, and the score is still low, so there is room for improvement. And when we train a SciBERT language model on the abstract only, that's what we get, like an F1 score of 26. That's our baseline. Okay. So our idea here is, so the abstract is too short, the full text is too noisy. Can we have a third representation? That's what we're trying to do. And our third representation actually is we'll ask a large language model, we'll give him the full paper, and we'll ask him to summarize this paper in a certain number of words. We'll provide a target length, and we'll say, can you summarize this paper? And this extended summary will be further used for a text classification task. That was my idea at the beginning. And why this would work, I said, because when we generate an extended summary by being careful in the length, we know that we can respect the language model size. We can be concept complete, so we can guide the LLMs to write the summary in a way that the core concept and the second concept of the paper appear in the summary. And this method also, like you at the inference, you will just basically provide the full text, you'll get the summary, and you will use this summary to perform the text classification task. So that's actually how it works in detail. So we have a full paper here. This full paper is very long, so it exceeds the limit of the language model. So I will separate that into different chunks. Chunk 1, chunk 2, each chunk have 3,000 words. And then I will use an LLM to generate a compressed version, a summarized version of this first chunk. It will generate it in like 200 words. And then I will pass to the second chunk. I will ask to compress it. But when I ask to compress this chunk, I'll provide as a context the previous chunk, so it avoids repetition, and the discourse, the way the LLM would write will be more fluent. And that's what I will do for every chunks. And then when I have all the compressed chunks, what I will do, I will have an LLM that will take all these compressed chunks, and I'll ask him to rewrite this summary in a fluent and coherent way by keeping all the relevant information in this compressed chunk. And then we have the final summary, which is budget friendly, let's say, that doesn't exceed the, yeah.
So with your chunks,
Mhm.
do you separate it just by, let's say, the first 3,000 words, regardless of where that falls, or do you separate it into the sections of the paper? So, for example, chunk 1 might be the abstract and introduction. Chunk 2 is the methods. Like, do you follow those?
Yeah, that's a very good question. Ideally, what we would do, we should split according to the section and the subsection of the paper, but we don't have in the full text we have, at least the dataset I had didn't have this structure. So I didn't know which paragraph was in what section, because I had like a full string that was a full paper. So I decided arbitrarily to chunk it at 3,000 words. But in the future, ideally, it would be better if we have the information of the section and the subsections. That's something we will explore in the future as well. So yeah, that's the whole methodology, how the papers are summarized. And then, just to give you an example of, to have an intuition of, like, let's say you have an abstract, and this abstract, they have a model will predict some keywords. You can see that the predicted keywords are very dependent, are heavily depending on the length and the content of the abstract. And when we have an LLM-based summary, some concepts that were not occurring in the original abstract written by the authors can appear here. So it can help the language model to predict more relevant keywords.
Yeah. I have a question about the chunk.
Yes.
So 3,000 words per chunk.
Mm-hmm.
Is this an artifact of the LLM you were using with the 4,000 context?
So
try it with, say, 1 million context LLM just as one pass?
I could have used, I tried several configuration where I actually give the LLM just the full text and ask to summarize, but it was always omitting several concepts. So this extended summary that we're generating wasn't very helpful and relevant for our task. So we had no other choice to separate into different chunks. Arbitrary 3,000. I could have maybe taken 5,000, 6,000, but I said 3,000. So the LM focus on always small paragraphs and not and to avoid omitting some relevant information. Okay, that's really fine. Thank you very much.
Summarize this, or do you?
Yeah, so the prompt is I'll try to remember my prompt. So basically, I instruct the language model to compress each chunk by actually, if you want, at the end of the presentation, I can show you the prompt itself. But we ask to summarize the chunk by keeping the relevant information, by avoiding repetition and not adding information that are not in the original paragraph. Yes.
Yeah, so one question, a couple of slides back, you were talking about like precision and recall.
Yes.
So for different problems, like people care about like high precision or high recall, and it's kind of like a trade-off.
Yeah.
Right? So for this particular task, where do you think you are in that?
I would say we're mainly trying to increase the recall because we are thinking from an information retrieval point of view. So we want to gather as much as information as possible. So we would say that we want the highest recall. That's what we're mainly aiming for, I would say. But of course, the precision as well. But since it's from an information retrieval point of view, we think to have more concepts. So it's better to be more comprehensive in the set of keywords we extract than maybe on the quality of the keywords. Yeah, I would say mainly the recall. Okay, any other questions or I continue? Okay, so yeah. Okay, so our experimental setup is the following. So we have the dataset that we released, which is composed of 21,000 astronomical papers annotated by the authors of the papers. We have among these papers like 1,700 labels that are used. In average, we have 4 to 5 labels per document. We split that into train, val, and test. We used BERT model for training the classifier to predict the keywords on 5 epochs. The input representation that we used is the abstract, the author-written abstract, the full text, the LLM-based summary, and this oracle that is. So the oracle is a theoretical. It's the ideal scenario where it's the highest score, highest performance we can reach, basically. And I'll say a bit more about that later. And our evaluation metrics are the precision, recall, and F1 score at different values of K. So to evaluate the quality of the prediction at the top 3 predicted keywords, top 5 predicted keywords, top 10, and so on. So yeah, here are the results. So when we look at the abstract, precision, so we'll look mainly at the F1 score at 5, because as I said, we have like usually 5 keywords per paper. So that's really what we really want to see. We can see that the abstract outperform the full text because the full text is noisy. It contains sections that are not necessarily relevant for our keywords prediction task, such as the related work section or the acknowledgement and so on. A lot of sections that are less relevant, like the methodology or the result sections. And also we chunk this paper. So that's an important fact. Since the full text is too long, we chunk it into, we split into different chunks, and our system is trained on each of these chunks. So he's seeing a lot during the training process. The model is seeing a lot of unrelevant chunks, and we try to force the model to predict keywords based on some chunks that are completely non-relevant. And when we look at the LLM-based summary, we can see that we outperforms the abstract and the full text. We can reach like almost 27, 28 in the F1 score at 5. And whatever the value of K, we are always outperforming. So yeah, we have almost like a 5% improvement at 5. The full text, as I was saying, is the worst, and the oracle. So how did I compute this oracle? So let's say you have a system that always know what's the best input representation. That's the oracle. For example, it's a system, an ideal system that will know, in that case, I should use the abstract because it has enough information. I don't need to generate a summary. And if the abstract is not enough, the oracle will know that he has to go to this summary. So he always knows what's the input representation. That's how I computed the oracle. So basically what I did here, for each document in our test set, I separately used all the abstract and all the summaries. I generated my predictions, and then I compared which one was giving the best F1 score, and that's how I got this oracle F1 score. It's a theoretical value, so it would be ideally, so to know what can we expect from all these other models, basically. Okay, and we have seen that in general, the LLM-based summary provide the best result. And then I was curious to see if this summary is better for the very rare labels. And we can see at the F1 score at 5, if we compare the abstract versus the LLM-based summary performance, we can see that we have a significant increase in the F1 score. So the rarest labels, the ones that occur less than 50 times in our training samples, benefit the most of these summaries. So these summaries, they provide additional signal that we don't find in the abstract or in the full text. That's a very positive results. And then, so yeah, these are mainly just the summary that our findings. So the input representation matters. The LLM-based summary provides better result than the abstract than the full text. And it's mainly the labels that are the most rare in our dataset that benefits from this input representation. And then I'll say a few more words about the oracle. So this oracle, as I said, is the ideal scenario. And I was wondering if this small gap that we have, this very tiny gap actually, that we have between the summary-based approach and this oracle, can we fill this gap? And because here we have approximately 74%, the summary already captures 74% of this theoretical upper bound. And I was trying to say, okay, there is still a small margin. Can I try to fill this gap? But how? Because how can we know in advance if we should use at inference, if we should use the abstract or the full text. And then I'm thinking that's still a work in progress, actually. I said maybe I can try to use the entropy as information to know if I should use the abstract or the LM-based summary. And here I will explain how does it work. So first of all, the language model will use the abstract to make its prediction. And I will look at the probability vector. Because the language model for each labels, the 2000 labels we have, it will provide a vector, a probability, a score. And I will look at, via the entropy, how these probabilities are spread. Are they concentrated or are they spread? Basically, what I want to say here, I want to see if the language model is confident when he uses the abstract as input representation. If, for example, he will give among the 2000 labels a high probability for one or two labels, a high probability, and almost zero for all the other labels, we can say that, okay, he is almost certain that these one or two labels that have the highest probability are the labels. But now, if you consider a case with a high entropy, so a model that is less sure about its prediction, how it would look like? It would look like maybe he has 50, 100, 200 labels with high probability. So he's not really able to decide what are the labels we should use. That's how I'm trying to quantify, and this is still a work in progress. So I don't have the result, but that's how I would like to process. So I can show, basically, that's what my idea is. I would like to compute the labels using the abstract and the summary, get this entropy score, so how concentrated or spread the probabilities are, and based on a threshold that I would fine tune on the validation set, I can try to decide at inference if the abstract was enough or should we generate a summary. Also, why I'm trying to do that, because when you want to generate summaries, it also has a computational cost. So just to give you an idea, when I have generated summaries, extended summaries using our 20,000 dataset, it took like approximately 4 days to generate all the summaries. So it's very expensive. It takes time. And at a larger scale, when we have a system in production on SciX to classify papers, it wouldn't be very viable if we always generate summaries, because maybe sometimes we don't need to generate summaries. So that's what I'm trying to explore. And in the future, other steps will be also to so the summaries that I generated currently were using Mistral large language model, but the quality of these summaries can change according to the LLM we're using. What about Qwen? What about Llama? And also the classifier I'm using was SciBERT. I can use AstroBERT or other language model to test. And as a computer scientist, I'm also curious if this methodology would benefit other disciplines as well, and not the astronomy, but also like the biomedical domain, where the scientists have the same are facing the same issues, or the computer science domain, the clinical domain, and so on. And that's it for me. Thank you.
Thank you so much, Atilla. And there were many questions during the presentation. Are there any extra more? Hi, I have a very general question, and it might be more of a question for everyone too, but like, I think the sort of test shows that like abstracts are, the full text is often, very pedantic and a form of documentation, right? And contains a lot of noise that's not actually conveying the full, that's necessary for documentation purposes and for reproducibility, but doesn't actually capture a lot of like the core science, while an abstract is often very forced, very short, kind of feels very unnatural. You're really only including like a couple topic sentences. And so I'm wondering if, you condense these summaries into a certain word count. I'm wondering if there's like, given I feel like publications haven't evolved a lot over the last, dozens of years. So I'm wondering if there's opportunities to use what you're developing here to try and figure out like what is an optimal length of, let's say if we did summaries instead of just, that could be abstract, but also if authors provided summaries of their work, mostly to communicate the scientific impact, and whether there's an optimal length for such summaries given like what is necessary to capture. Because some fields definitely will be like, oh, we can do it in 2 sentences, and others are like, I need 2 pages. I don't know. So that's sort of more addressing publications as a whole, not your project in particular, but it's an interesting thought.
Yeah, I know. I agree. Thanks for your comment, and I guess that would be. That's what I would like to hope. Like that, my work serve as that we have a finding, and maybe it can help the community to adopt new practices. So that can be very good. That's what I would like to achieve. Yeah.
Yeah, that's very kind. All this, how do we handle public?
There was also 2 questions.
Wait, you were first.
Very nice talk. Many papers have conclusion sections, so if you try doing a comparison with your summary conclusion section, and just following on that comment there, I think this would be a nice tool for helping astronomers write better abstracts, and often people resources by the end of writing the paper. But
True. Yeah, about your question, like regarding the conclusion, I'm also conducting currently an ablative study where I try to identify what's the best section of the paper. So I'm trying different system where I use only the abstract plus introduction, and plus the methodology section, and try to remove and add sections, find different combination, and train the system on these to identify what are the most relevant sections. But I didn't try it with the conclusion only. That can be also actually something, because it retake information from the abstract, the introduction, and the main findings. So I didn't try the conclusion yet because I'm still in process of doing this ablation, but that's something very interesting to look for.
So have you thought about multimodal data, right? So what if you train, because you were saying that you're just chunking based upon the string of text, right?
Yeah.
But what happens if you also train on like figures, for instance?
That's true, because actually the full text that we're using doesn't take into account figures or formulas or tables, or depend on the tables. But that's true that these are type of information we omit for the moment voluntarily. But it can be very interesting to include this information, to keep them and train maybe a multimodal system and see how what's the benefit and information we can get from this type of data actually. That's a very interesting idea.
I have a second question. I'm bootstrapping off of what they were talking about. In that your summaries are built to essentially be optimized for a classification scheme, right? But it's not necessarily for the way we normally write abstracts. So if you look at these summaries, is it just the level of detail? Are they structured differently? Like what is it that's providing a better classification scheme than our normal way we write abstracts?
Yeah, I would, very good question actually. So I would say because when I generate the summaries, I explicitly request the LLM to, I tell the LLM that the summaries that you're generating will be used for text classification task. So the LLM, the way he will generate the summaries, he will maybe add some concepts that the authors didn't add initially. So we have more signal that will come from there. That's what I would say, because we explicitly tell the model that this will be used as a text classification task with a taxonomy, which is the UAT and so on. So we are really guiding the system to provide a representation that is relevant for us. And the author, like when we submit a paper, we don't necessarily think about this task, and we just put keywords and that's it.
Thank you.
So you said that you're this input text. Does it take into account like the paragraph structures? Because like as a human reader, the structure of the paragraph, when a sentence breaks and a new paragraph starts, that conveys information. Is that?
That's a limit of our work. Currently, it doesn't for the moment. And ideally, in the next couple of weeks, in my next experiment, that's what I'll try to include in the experiment. And I expect to have an improvement when we take into account the structure of the paper.
Anyone else? Anyone online? Okay, well, great.
Thank you
We
very
have a lot
much.
of discussion, and thank you so much.
Thank you. Thank you. Thank you. So I can